Gas and dust in the Milky Way. Building blocks of the galaxy. The Milky Way is more than just a collection of stars. It is a dynamic and intricate system that includes vast amounts of gas and dust. Together, these components form the interstellar medium, ISM, which occupies the space between stars and plays a critical role in the galaxy's life cycle. Gas and dust are not only the raw materials for star formation but also key players in the dynamics, evolution, and appearance of the Milky Way. What are gas and dust in the Milky Way? Gas and dust in the Milky Way constitute the primary elements of the ISM. They are present in different forms, temperatures, and densities, influencing both the physical processes and the observable characteristics of the galaxy. Gas in the Milky Way. Gas forms the majority of the ISM by mass and is composed primarily of hydrogen and helium, along with trace amounts of heavier elements. Depending on its state and environment, interstellar gas can be classified into several categories. 1. Neutral hydrogen, HI. Characteristics. Neutral hydrogen is the most abundant and widespread form of gas in the ISM. It is typically found in diffuse, cool regions of space. Detection. HI gas is detectable via the 21 centimeters radio emission line, which occurs when the spins of the electron and proton in a hydrogen atom align or flip. Role. This gas forms the foundation for the eventual creation of molecular hydrogen and stars. 2. Molecular gas, H2. Characteristics. Molecular gas is found in the densest and coldest regions of the ISM, where hydrogen atoms combine to form molecular hydrogen, H2. Molecular clouds. This gas is concentrated in giant molecular clouds, GMCs, which are the primary sites of star formation. Detection. Direct observation of H2 is challenging. Instead, astronomers use tracer molecules like carbon monoxide, CO, which emit detectable radiation in the radio and millimeter wavelengths. 3. Ionized hydrogen, HI. Characteristics. Ionized hydrogen exists in regions of high-energy radiation, typically near hot, young stars. HI regions. These regions are luminous and visible in optical wavelengths, such as the famous Orion Nebula. Significance. HI regions mark areas of active star formation and illuminate the surrounding interstellar medium. 4. Other gases. Helium. The second most abundant element, helium is found in all phases of the ISM. Metals and molecules. Heavier elements like carbon, oxygen, and nitrogen, along with complex molecules like water, H2O, and ammonia, NH3, enrich the ISM, influencing star formation and interstellar chemistry. Dust in the Milky Way. Interstellar dust, though constituting only about 1% of the ISM's mass, has a profound influence on the galaxy's processes. 1. Composition. Dust grains are composed of silicates, carbonaceous materials, and ice. Sizes range from a few nanometers to micrometers, comparable to the wavelengths of visible light. 2. Distribution. Dust is concentrated in the galactic disk, particularly in spiral arms where star formation is most active. It is often intermixed with gas in molecular clouds and diffuse regions. 3. Properties. Extinction and reddening. Dust absorbs and scatters starlight, causing distant stars to appear dimmer and redder. Thermal emission. Dust grains absorb ultraviolet and optical light, re-emitting it as infrared radiation. Catalytic role. Dust surfaces facilitate the formation of complex molecules, including molecular hydrogen. Distribution of gas and dust in the Milky Way. The distribution of gas and dust is not uniform and reveals the structure and dynamics of the galaxy. In the galactic disk, the majority of gas and dust is concentrated in the thin disk of the Milky Way, particularly in its spiral arms. The Sun resides in the Orion Arm, a minor spiral arm rich in gas and dust. Star-forming regions are often found where gas and dust are most concentrated. In the galactic halo. The halo contains a much smaller fraction of the ISM, primarily in the form of hot, ionized gas. Dust is scarce in the halo compared to the disk. In molecular clouds. Molecular clouds, often called stellar nurseries, are dense, cold regions rich in molecular hydrogen and dust. Examples include the Orion Molecular Cloud Complex and the Carina Nebula. In diffuse clouds are less dense and contain a mixture of neutral hydrogen and dust. These clouds serve as transitional zones between molecular clouds and fully ionized regions. In interstellar filaments, filamentary structures in the ISM, often composed of gas and dust, act as conduits for material flow and star formation. Role of gas and dust in galactic processes. Gas and dust are fundamental to the Milky Way's life cycle, influencing star formation, galactic dynamics, and chemical enrichment. 1. Star formation. Molecular clouds as stellar nurseries. Star formation begins in molecular clouds where dense regions collapse under gravity. Role of dust. Dust grains shield the interior of molecular clouds from ultraviolet radiation, maintaining the low temperatures necessary for star formation. Feedback mechanisms. Newly formed stars heat and ionize surrounding gas, creating HI regions and driving turbulence. 2. Chemical enrichment. Stellar evolution. Stars enrich the ISM with heavy elements through stellar winds, supernova explosions, and planetary nebulae. Metallicity. Gas and dust in the ISM incorporate these elements, increasing the metallicity of subsequent generations of stars. 3. Energy transfer and regulation. Dust grains absorb high-energy radiation and re-emit it in infrared wavelengths, redistributing energy within the galaxy. Supernovae and stellar winds inject energy into the ISM, driving turbulence and influencing star formation rates. 4. Galactic evolution. Gas accretion from intergalactic space and mergers with satellite galaxies replenish the ISM, sustaining star formation over cosmic timescales. Outflows driven by supernovae and stellar winds regulate the galaxy's growth by removing gas and dust from the disk. Observing gas and dust in the Milky Way. Studying gas and dust requires observations across the electromagnetic spectrum. Radio observations. Neutral hydrogen emits a characteristic 21 centimeters line detectable by radio telescopes. Molecules like CO are studied using millimeter-wave observations, revealing the distribution of molecular clouds. Infrared observations. Dust emits strongly in the infrared, making it visible to telescopes like Spitzer and JWST. Optical observations. HI regions and emission nebulae are visible in optical wavelengths, revealing sites of active star formation. Absorption lines in stellar spectra provide information about gas and dust along the line of sight. X-ray observations. Hot, ionized gas in the galactic halo emits X-rays, observable by telescopes like Chandra and XMM Newton. Ultraviolet observations. Ultraviolet telescopes detect hot gas and study the effects of radiation on dust and molecules. Challenges in studying gas and dust. Studying gas and dust is not without difficulties. 1. Interstellar extinction. Dust obscures optical and ultraviolet light, making it difficult to observe distant regions of the galaxy. 2. Complex dynamics. Gas and dust interact with gravitational forces, radiation pressure, and magnetic fields, creating turbulent and chaotic flows. 3. Three-dimensional mapping. The vast size of the Milky Way and the overlapping structures of the ISM complicate efforts to create accurate maps. 4. Tracer limitations. Indirect methods, such as using CO as a proxy for H2, have limitations and introduce uncertainties. Recent discoveries and future directions. 1. Galactic winds and feedback. Observations reveal powerful outflows of gas and dust driven by star formation and central black hole activity. 2. Interstellar chemistry. Discoveries of complex organic molecules in molecular clouds are providing insights into the precursors of life. 3. Star formation efficiency. Studies aim to understand why some molecular clouds form stars more efficiently than others. 4. Next-generation observatories. The James Webb Space Telescope, JWST, and upcoming radio arrays like the Square Kilometre Array, SK, will revolutionize our understanding of gas and dust. Conclusion. Gas and dust are the lifeblood of the Milky Way, fueling star formation, shaping its structure, and driving its evolution. They act as both the canvas and the paint for the galaxy's dynamic processes, offering a glimpse into its past, present, and future. As observational technologies advance, our understanding of these fundamental components will deepen, revealing new insights into the workings of our galactic home.